AI is probably not the first technology that disrupt markets. However, I think this time it's a little bit different because we start seeing that that it's not about single job that is being maybe replaced by technology. It's more about the entire groups of people, or like knowledge workers. I think a new world is coming. What we know from 5 years ago won't be really the case in the new brave world. So when I started working with LLMs, nobody knew what LLM is. I had to really spend a lot of time to actually explain my colleagues from outside of work and also my family of what I'm actually doing and how these things work. Whereas like fast forward just these few years and it's on everybody's mouth, right?
Everything can be turned into numbers. Does it mean that everything in the world is a pattern?
It could. We could, like, if we start looking at events, things that happen as basically outcome of a certain process that is perhaps governed by some distribution that we might not know about it, then yeah, everything could be seen in these slides. I think what LLMs are missing is that they are just learning from text. They're learning the apple is tasty, the apple is red, all right? But they only know it from text, whereas we humans, we can interact with the world. We can touch this apple, we can taste it, you know? So there's just so many different signals that can come from just interacting with the real world that is just so hard to embed within text so the models can learn this. I mean, language is not ideal way of transferring knowledge. The real world is like a continuum. So we just came to this world, and for us, in order to understand it in a better way, we started categorizing them and giving labels and domains and stuff. But like the world doesn't really work like this. It's a continuum space. Whether consciousness is actually important at all, maybe this is something that is not now we are dealing with and struggling with to understand. Maybe it's not even important for AI to be really efficient and productive and to take over the world. Like I said, yeah, very metaphysical stuff, but
Hi, Jacek. Thank you for being here.
Thanks. It's my pleasure to be here.
So today we talk about AI, the hottest topic of of the 21st century, probably. And you are an expert in AI. Could you please briefly introduce yourself for our audience?
Right. So I'm Jacek. I'm a former machine learning large language model researcher at the Humboldt University. My research focus was mostly on the knowledge representation in large language models. Basically, how we represent knowledge, how the knowledge is represented in large scale language models like LLMs, GPT, and so on. So specifically, I was focusing on studying the acquisition of knowledge, how the models learn new, not factual knowledge specifically, or relational knowledge, and then also how they forget. So specifically, when you have a model and you're continuously updating it with new knowledge, I was studying how this knowledge is being forgotten, how it's being integrated, and so on. This was my research focus, but currently I'm co-founder and sitting at the board of advisors for BeeARD, which is a project that is tasked with autonomously generating scientific hypotheses. And recently I co-founded LUPA, which is a research platform for scientists that uses AI natively in order to help them with their work, streamline the process of coming from idea to writing basically a manuscript. Both of these projects are at the intersection of AI and science.
Why did you decide to focus on AI for science specifically?
Right. Actually, I think an important moment in my life happened last summer. I was actually working on one of my publications when I read a paper by Sakana AI. It's this company from Japan, and they wrote a paper called AI Scientists, where they described a new system of agents that autonomously work on creating new research, specifically in machine learning. In this system, AI agents were able to first come up with their own hypotheses, then find literature and conduct a thorough literature review, then conduct design experiment, perform this experiment, and analyze the results, and then basically write this all in one paper. So for me, this is really eye-opening because I realized that you can also work on papers and do kind of be adding your own research to the pile of research, but also you can actually work on the underlying process itself, which I found this to be much more impactful, where actually I can work on the evolution of how AI evolves with science. I realized this is much more impactful thing to do for me at this moment. And this changed my career. I decided to not work at the university anymore and start first BeeARD and now.
I want to pull a question out of your self-presentation. You said that your research was originally focusing on how LLMs learn and how they forget. So if you will simplify that for more or less dummies, how it happens, I'm sure that people would be interested to learn about it.
Right. So the current language models, or large language models as they are called, due to their really large size of parameters, the way they are, they're first of all, they're based on transformer architecture. This is this specific architecture that is used in machine learning and is widely used when we are working with text. This basically took all of the big models, so ChatGPT, models from Google, Gemini, they are built as a transformer architecture, and they are trained on so-called next token prediction. So basically, they also refer to as autoregressive language models because they basically learn to predict the next token in a sequence of tokens. Tokens, you can think of a token as a word, but it doesn't necessarily need to be a word what we think. It might be a part of the word. But yeah, for all the purposes and for our discussion, we can just think of it as a word. So what the model is tasked with is basically by trying to learn statistical distribution of these tokens, and it learns the next token in a sequence. So when we have already a model that already is trained on large amount of text, and for example, we want to fine tune it on a specific domain. Let's say we have a model that is being trained on general data from the internet and that acquires all of these skills, like acquires understanding of how basically language is constructed, the syntax of the language. Basically what tokens follow which ones, or like what words are following the other one. And we want to we want to take this generic model and fine tune it on more domain specific data. So for example, in science, you might want to train it on scientific publications. So in order you can understand better the words, the vocabulary that's used in science, because it might differ greatly from the general texts that are found on the internet. And also because of this, the distribution of weights, distribution of how it would assign a specific probability to a next token in a sequence is also different when we talk about general text on the internet and the scientific data. Right, so then you take this generic model and you want to fine tune it on some more domain specific, like maybe longevity data or longevity papers. And so what we were doing, for example, is taking the models, off-the-shelf models, then continuously pre-training, meaning we were exposing these models to new data that they were not trained on, and while they were while we were adapting them to a new domain, we were observing what are their performance on specific tasks. Specifically, we're looking at the tasks, like the general tasks that we could measure with more general benchmarks that you could think of. They were optimized in the previous pre-training phase, and then looking how this performance changes over time when we are adapting to a new domain. At the same time, looking at how the performance on this domain-specific task, like for example, answering questions about longevity, changes while they are learning this new set of documents from this new set of documents. And so this is what I mean by observing how they are learning and forgetting.
Why we're even able to take a model from the shelf and apply it to a completely different domain, let's say not text, Can I use it for, I don't know, protein folding or whatever? I mean, large language models are following the laws of statistical distribution. Yeah, so we have this huge data set, we feed it into the model, processes all of that, and says, okay, most likely next token will be this one. So why we can do the same for, I don't know, biology or something else? For words, it's obvious. Yeah, because it's a language and you can predict the next letter. It's quite simple. But what about other types of data?
Well, so I think it's mostly about the representation here. So text, but also audio and images as well. We can represent as sequences. Specifically, maybe it's super easy or like super intuitive to think about sequence, what we have in audio, right? And when we are dealing with sequences, then we can also, what we are trying to do is find underlying patterns in the data to approximate this distribution that might be governing the process. Right. So I think it's not really about the specific words here. I mean, like what we are dealing under the cover are still vector spaces, right? So like the words are actually turned into a numerical representation, and what we are dealing are actually just numbers that go into the language model in the form of a sequence. So if we can represent anything as a kind of a vector, perform this, we are trying to learn this underlying statistical distribution that governs a certain process, then it's not so important what specifically it is for us humans, but how we can represent it for machine learning models.
But literally everything can be turned into numbers. Does it mean that everything in the world is a pattern?
It could. I mean, there is like if we start looking at events, things that happen as basically outcome of a certain process that is perhaps governed by some distribution that we might not know about it, but maybe it's still somewhere there, then yeah, everything could be seen in these slides, in this framework.
This is super interesting and even a bit philosophical, but let's go back to AI for science and research. So you were inspired by this idea that it's possible to create AI agents to perform full-scale research, to create hypotheses, to work with research papers, to come up with new ideas. So currently it's very popular. If you go on LinkedIn, AI will take our jobs. So do you think that with the newly born army of AI researchers, human researchers should worry about their positions or not?
Yeah, so I think that's a very fascinating question, and I don't really think we have an answer to this yet. You know, there are some analogies from the past. I mean, AI is probably not the first technology that disrupt markets. Although I think this time it feels a little bit different than what it was in the past. Maybe like an example from near is where the ATMs were coming to the market. And so many bank tellers were actually afraid they might lose their job. And what happened was that actually by introducing ATMs, in fact, it was that many people started using ATMs and not so many people were needing the help of bank tellers. But at the same time, running a bank branch became way cheaper because you didn't have to have so many bank tellers, right? So because it became cheaper, then you could create more of the branches, and then this kind of like a net effect was completely different, right? And this was still in the 80s. And like when we look at this right now and how it advanced, everything, like now we don't really use it. I mean, depends on the location you're probably in, but I know in Berlin it's a little bit different, but like in a lot of places, you don't really use cash so much, you know? So, I mean, like, this is like huge shift. Like, technology started this shift and it didn't really eliminate jobs. They changed the nature of their jobs and changed the distribution of it. But it didn't really kill jobs specifically, meaning I think the previous technologies that disrupted the market, mostly just changing the type of jobs you could do. So people who were able to adapt to a new environment, new reality, they were also part of the job market still. However, I think this time it's a little bit different because we start seeing that that it's not about single job that is being maybe replaced by technology, by computers or by ATMs, etc. But it's more about the entire groups of people, or like knowledge workers, because we can have AI systems that can reason, that they can make decisions, which is pretty broad aspect of jobs, right? So personally, I don't think people should be so much afraid of their jobs as long as they're willing to adapt to a new reality. But definitely, I think a new world is coming. What we know from 5 years ago won't be really the case in the new brave world, but it's more about how it would evolve, and maybe it's about rethinking what a job is as well. Specifically for scientists, I think also this role would evolve, maybe from more of this mechanical work where you actually have to spend a lot of time on this tedious work or repetitive stuff, like doing literature reviews, searching for papers that might be relevant, doing data analysis. I mean, we might be start migrating towards this role of an artist, almost like an orchestrator that is just using AI as an instrument to explore the world. But things that are really important in science, like curiosity, I think they will be still driving force behind this scientist version 2, maybe. So I think like there will be still space for scientists, but I definitely think this role would evolve like many other roles in post-AI world.
I agree with you. But what about entry-level positions? Because it's a big question right now. Folks who are in the industry for 10, 15 years, they actually feel a better and a bigger impact on their productivity when they use AI. But young specialists straight from the college or university, they can be fully replaced by AI already. And I think it's happening because in accounting, in marketing, lawyers as well. So they stopped hiring young people, Gen Z, and younger, because they just don't need this workforce anymore. And that leads to the fact that there is no knowledge transfer between the generations, and you just don't have this fresh blood coming in the industry. What do you think about it?
Well, yeah, I definitely heard about this as well. And I mean, maybe it's really hard to say on such a short scale if this is going to be really a trend. So I've been also hearing some trends which goes against this, that first the company kind of fired a lot of the software engineers and they started rehiring them afterwards. So I think like maybe the time scale right now we are operating is really short to really be able to have really grounded focus for the future. However, I think like AI can have like, okay, so obviously with the current state of AI and the agents or like AI based or like LLM based agents that can really make their own decisions and operate, use the internet, use the computer actually to perform different tasks. I think the knowledge workers, the need for knowledge workers is falling down, like the demand for knowledge workers falling down. So we might actually see that all in all, there will be less positions for the jobs that we know of or that we already got used to it over the years, right? But it doesn't really mean that there will be no new jobs that will come up with this. I mean, I think it's a little bit too early to say. But what I wanted to say is that actually at the same time, like it makes like the senior workers, senior employees much more productive so that they don't need a junior developer, for example, to employ a junior dev because they actually can use two AI agents that would be kind of like a junior dev. But at the same time, you can actually use AI to learn a lot. You were mentioning that there's now this generational transfer. And if you start looking at LLMs and the knowledge that is contained in them as a way of transferring this knowledge, basically anytime you want. So you can actually you don't really need so much money now. You don't need to know specific people to actually learn so much on your own if you have a drive for this, right? So I think at the same time it will be harder to get to these entry-level positions for the jobs that we are currently used to, so these are the jobs still from the old system, but we are entering a new world where there will be new positions, new roles as well. This could be completely different. There might be a huge demand for these roles. It may be sometimes hard really to think of them right now. But at the same time, like the artificial intelligence and the LLM specifically, they empower so many people who would not be able to do it to just learn these things and really master quite a lot of skills by using AI. So I think it's really hard to say what would be the net effect of this. It seems like it's gonna be harder for entry positions, for the entrance to the to people who are entering the market and looking for the positions that we are currently having on the market. We are kind of living this experiment right now, where everything is changing, and I guess we have to see a little bit more to be more confident.
Hopefully so, because for me it seems that even CEOs of huge companies, they have no idea what happens. That's why they're making weird decisions like firing 5,000 people, rehiring 5,000 people
Yeah.
without for everything. No, we only use AI for this specific task. No, we don't use AI at all. And that just changes every day.
I mean, this is a live experiment. So when there's an experiment where early in stages of basically anything, there's a lot of experimentations by basically kind of trying to see what works and what doesn't. And yeah, we're just so early at this stage that I think a lot of things will become a little bit more clear in the near future, or maybe a little bit longer. But yeah.
The future seems very near because AI, I think, has the steepest adoption curve in the known history of humanity.
Right. I mean, maybe that's why everything feels a little bit different as well, because before this disrupting changes took longer time to be implemented, to be adopted. And AI is literally like a steep curve that goes up on actually every dimension now. So it also probably adds why it feels different this time. But yeah, we'll have to wait a little bit to see how it unfolds, this live experiment.
Do you believe in technological singularity by 2029, I think?
From what I saw, there's like entire spectrum of different predictions. Some of them are more bullish, some are more conservative. Do I believe in singularity before 2029? I think in
Or it
my
was AGI, I think.
AGI, yeah. I mean, also like, yeah, it probably also depends on the definition of AGI specifically, where this is more like it's exceeding human capabilities. Personally, I'm a little bit more on the skeptical side, but I'm still quite amazed with the progress that happened over the last few years. So when I started working with LLMs, nobody knew what LLM is. It was not really near any understanding of. I had to really spend a lot of time to actually explain my colleagues from outside of work and also my family of what I'm actually doing and how these things work. Whereas, like, fast forward just these few years and it's on everybody's mouth, right? So the progress is incredible, and sometimes it's really hard to predict of how fast it's gonna go, whether we gonna maybe hit a certain the acceleration, especially in terms of the architecture we're using, or whether this is still gonna continue on this acceleration as we have seen for the last months and year or two. Yeah, so I'm more on the skeptical side. I'd probably say it's not gonna happen in 2029.
But it will at some point, or not.
Yeah, I think there's a really large chance. I mean, I would, I would believe it will. I'm not so sure about the date. Yeah, many smarter people than I am already predicted these dates, ranging basically from 2026 or 27 until 2035. So it's around the corner, you could say. We have to see whether we can actually achieve this with the current architecture and the current way of basically training language models or not. I mean, the voices they're diverse voices in regards of whether we can achieve this with the current technologies that we need to do. Maybe by the time everything, by the time the editing of the podcast episode will be done, the GPT-5 would come up and everything would be different, and maybe we already have AGI by then.
Maybe we already have an AGI, just hides itself.
Yeah, maybe things are going so quick that.
Well, yeah, but how about, running out of data? There is also thought about running out of data, and there is also very interesting research on embodied AI that actually pulls the information from the outside world.
Yeah, I think this is really important part. So I think maybe touches a little bit on basically the bottlenecks we have right now in researching, in advancing AI. So I think a couple of years ago, or maybe even like just recently, 2 or 3 years ago, asked me what are the problems, or like what are maybe the bottlenecks of research in AI or advancing AI. I would say it's probably the compute. And not to say it's not important part at the moment. I think it's just not the most important part we have right now. So there has been a lot of investment from tech giants in building these big centers for training models, and we are approaching the moment where we're starting having problem with data. It's not only about the data, but about good quality data. So there's saying in machine learning, garbage in and garbage out. I mean, if you train your model on really poor quality data, you might also get really good results.
What is poor quality data and good quality data? What does it specifically mean?
Right. I mean, just looking at maybe the data that's being used for training language models, so text, they're usually scraped from the internet, and you can have an article about the same event, just written completely too differently. One actually can have a lot of biases, for example, right? That is just not really truthful, contains biases from a person who writes. Maybe there's a lot of also infactual or like infactual statements. So this is definitely poor quality data. Whereas you can have the same article written in a more informative way where facts are straight. So I would personally think this is just much higher quality data, like in models. So this is mostly for pre-training. This is how models are pre-trained on these large data sets, but also something that is actually being used quite often is the post-processing part, where basically we take this very raw language model and we align with human preferences. This is why like models like ChatGPT or Gemini are so helpful, because they align with what people want. And this is also being trained on data. Basically, they have human annotators that are also producing text, which are then used for training and supervise training and fine-tuning of this raw model. So also like this so basically how it follows instruction. Like you can actually you can have a question, and then the answer that the model gives is not really comprehensive. It's very unorganized, so you don't really see how from the premises you could end up with these conclusions, right? And this might be actually because it hasn't been really written. But then you can have really high quality data produced by very smart people working at the university that actually really know how to operate with text, and the way they present the information is very clean and clear. So this data obviously would using this data would end up. Yeah.
And we run out quite quickly of good quality content.
Right. So there's a lot of text on the internet, but as you can,
Some of it already know.
but you can probably imagine it's not always of the highest quality. And this is the easiest one to get because it already exists there. But specifically for the needs of training LLMs, specific data is needed, especially for post-training that has to be created. So basically, and humans have to answer some questions that can be used later on to train models. So this all data has to be created. It cannot be just scraped. So yeah, this is something that, and for example, recent success, or like maybe not so recent, but like one of the biggest companies in machine learning is Scale AI, that is just producing data for training. This is how important it is in making AI better models. So I think Meta just recently bought 49% of Scale AI.
Yeah, last week or 2 weeks ago.
A really a large sum of money, having good quality data and having access to good quality data that is basically created by humans.
Do you think LLMs are this final step of artificial intelligence, or there will be something else, maybe not large language models, but some other kind of models?
So I think that this is a pretty complex question. Like there are many disagreeing opinions about this aspect. There are people, some who are saying that we can probably get with LLMs with the current architecture to AGI, because LLMs by learning, by being optimized with the next token prediction function, they already have to build an internal model of the world in order to be able to predict the next token well. Maybe in the sentence, the ball fell from a table, and it is, and that, so this LLM would have to fill this one word, the last word, right? And then meaning like ascending or descending, right? So by having some internal knowledge of how world works, you would know because of the gravitation, the ball has to fall and not go up, right? So this is like what they mean by if the model is about to predict the next world, it has to have it also learns this internal world model. But there are also voices, and like Jan LeCun, one of the grandfathers of deep learning, is one of them, who is saying that this is definitely not enough because LLMs are fundamentally just learning text, and they don't learn from any other modality like vision, from senses, right? We have this limiting factor in what they can really comprehend and what kind of internal model they can learn. And even there's there are many, many different studies, and probably you tell me the hypothesis and I will find a study that confirms this or not. But speaking about this specifically about these internal models, there was recently this MIT paper that they just basically showed that even when model can learn perfectly directions within a city, they were asking, if I remember correctly, LLM to give directions in New York City, basically from getting from place A to B, and it had like amazing accuracy. Like it gave you really good way of getting from A to B in a city. But then once they make a problem just a little bit more difficult, so basically they close one road or two roads on the way, so the model couldn't really go this very learned path. It had big troubles of actually offering any solutions. So what they infer from this is that they actually are not building such a good internal models of the city here. Once the problem is a little bit more difficult, not like so framed ideally, then the model is having problems. And once you have an internal model, you'll be able to know, okay, I cannot take this road, but there's another road I can take, right? So personally, I think we probably might need to start exploring with other architectures and other models to be able to get further. Specifically, I think what LLMs are missing is that they are just learning from text. They're learning the apple is tasty, the apple is red, all right? But they only know it from text, whereas we humans, we can interact with the world. We can touch this apple, we can taste it, or we can taste it, maybe also break our teeth on this because it was really not ready yet, right? So there's just so many different signals that can come from just by interacting with the real world that it's just so hard to embed within text so the models can learn this. I mean, language is not ideal way of transferring knowledge. It's ambiguous. It's not ambiguous. Yeah, exactly. So it's not the ideal way of learning about the world. And LLMs, for now, they only really process text, well, also images as well. Transformers can process images. But I think it's still far away from being able to actually create these internal world models that are of high quality. And I would expect that we might need to go somewhere else. I mean, still LLMs are great, and they might be used in some architectures or like as a part of a bigger systems that can achieve this. And they are definitely great at what we are using them right now. So basically, these great text processors, they can really process text really well, they can understand it. And since a lot of our interactions in this world are actually text-based, I mean, this is a great tool that literally helps supercharge your work if you know how to use it. Yeah, so definitely they're great tools, and I would say we probably need something different in order to advance AI capabilities as a humanity.
However, science definitely produced a lot of words that you can use and process with AI. And if we go back to the topic of AI for science, what are the most prominent ways, in your opinion, how AI can and will accelerate the scientific progress?
Right. I would say like the three features that AI can really right now bring to the table is the speed it operates with, the scale, which is also connected with the speed, and this ability for cross-disciplinary links. So the speed is because it can work 24/7, all the time, as long as it has electricity. And the scale is because it also is connected with the speed, but it can just do much more processing of text. It doesn't really get tired. It can process way more information than we can. And with this is also connected this cross-disciplinary scale it can operate, right? So specifically, I think AI is now used extensively in brute forcing, looking for basically matches in combinatorial space. So brute force search is big aspect we can use it for. But also, I think because of the scale and the speed it can operate with, it enables us to start looking for and finding these hidden connections in the data that we humans already created.
Tell me more.
Right. I mean, there's just so over the last years, but this is already a process that started a while ago. I mean, the scientific progress is really profound, and just by looking at how many papers are being prepared every year, we have like over 3 million papers that were published in 2022 alone. It's just incredible amount of data, right? And like also at the same time, we as scientists are specializing more and more in the specific domains that we are operating with, just because there's just also so many papers, right? So when I was working in machine learning and focusing on LLMs, like every day there was just so many papers that were connected with what I was doing that I couldn't even think about started looking for interesting things outside. I was just having problems already by just analyzing the current state of my own little niche. And I think because we create so much data, we create so much paper, we create so much discoveries, there's just so much room for connecting the dots between different disjoint areas of research. Right. And this is by looking at the interdisciplinary, like the borders of sciences. So let's say how longevity is connected with psychedelic science, right? Maybe not something at first you would think of, but there's just so much knowledge that could be sitting around these borders of scientific domains that are waiting still to be just connected. And what I think is at the current state, we can definitely use it with AI because of the speed, scale that it comes up with. That we can reanalyze a lot of papers with a really high speed and throughput to actually start looking at these understudied interdisciplinary connections.
Do these connections even work? I wonder.
Because I think the real world doesn't have a border between something that is we as humans considered a longevity or right. I mean, this is like a continuum. So we just came to this world, and for us, in order to understand it in a better way, we started categorizing them and giving labels and domains and stuff. But like the world, it doesn't really work like this. It's a continuum space. And so having this in mind and having in mind that we are really focusing on our niches, so many times there might be discoveries that are related, but because we are focusing on specific parts of it, we might even be using different vocabulary for this. So different domains are having different vocabularies for the same things. This is how disconnected I think sometimes science might feel. Whereas, as I mentioned, this is not really a discrete space, but it's continuum space of like the world is continuous. It's not really discrete. So, and there's just not so much time for people who are like really focusing in their own niche and doing the research to really start looking at many other domains, see inspirations for research, because there's just so many of them, right? Maybe it is possible on a small scale, but like on the global, like multidisciplinary scale of all the scientific domains, it's way harder. So maybe that's one of the reasons.
I agree, but I have a technical question. If there are, let's say, two different domains with different vocabulary, with maybe studies that can be somehow interconnected, how would you, or maybe you already do that, maybe you cracked this nut, how would you connect these two seemingly disconnected topics, if the vocabulary is different, you need to operate on the level of a meaning. Is it possible or not?
So that's how, to a large degree, LLMs work, right? What happens with words that they are embedded into vectors, and these vectors live in high-dimensional space. Words with similar meaning used in a very similar setting, they will be having a very similar representations in the vector space. So the LLM,
I will forget. So you mean that terms in different, let's say, industries, in different fields of knowledge that have similar meaning would have similar patterns of usage, which would allow you to identify them?
I mean, I'm not saying this is given or that's how it always works, but meaning LLMs are not just looking at words, but they semantically and contextually understand them. So because we are also embedding these words into this high dimensional space, different words with a very similar meaning, they can be living very close in the space. Obviously, this differs from case to case, but in general, this is how it should work. There's this distributional hypotheses that basically words that are used in a similar way, they will be clustered in like similar spaces in this domain. So LLMs, they come with their own kind of world ontology. They can, to a large degree, obviously depends on the data they were trained on, quality data, right? If you have the diverse set of text, or is it just coming from Reddit, or maybe from Reddit, Wikipedia, and scientific publications, then you can actually have the same term used with different words, but the meaning stays the same. So then the LLM can actually learn, okay, there may be different tokens for this specific concept, but people are using it in a very similar way, or they're describing it, how it works, or where it may be applied in. So this is like they can live close in this space. So they are like semantically similar.
So it's technically a clusterization of some kind, yeah?
I'd say so, because we're not actually trying to find any clusters. We're just placing these words in this high dimensional space of vector space. Obviously, yes, or things that are semantically closer to itself, like maybe brother and sister, they might be living closer in this space.
Mm-hmm. Mm-hmm. Yeah, I understand. That's super interesting. And how you can use this to automate, let's say, the hypothesis generation process, or use this interdisciplinary knowledge to do that.
Right. So, okay. So, like, just to clarify everything what I said before is like that LLMs can semantically understand text. And like when there is a new word, they should be able to figure out basically how semantically similar it is to other words, even if it didn't know it before. So basically LLMs have this semantic understanding and contextual understanding of words. And then this is on a very low level. No, this is on a very high level. So maybe I can tell you specifically how we use it.
Yes, please.
So what we do is we create research papers and we turn them into structured representation. Basically, what we're trying to do is extract facts or scientific facts from these papers and convert them into a knowledge graph. A knowledge graph is the structured representation of knowledge. So you could think like there's a sentence that describes a certain process, and this is in the paper. This is written in natural language, so this is a more beautiful way of representing this information. But you can also condense this information. Basically, X causes Y, right? So this is the structured representation of a specific natural sentence. What we do is we turn these papers into these atomic, they're called triplets. So basically this atomic representation of facts. X causes Y, Y is subtype of Z, Z is associated with XYZ, for example, right? So you can actually turn this scientific information into this more structured representation. And then this from one paper, but you can do it on a much bigger scale. And this is basically what we do. We are basically trying to map scientific knowledge into this knowledge graph representation. Knowledge graph is a really interesting structure for LLMs to use because they can actually use it as a more of a like external memory, because this facts in knowledge graph are usually verified, easy to traverse, or easy to access this information. Often knowledge graphs are also used as these external memories. Specifically, what we are doing is we treat knowledge graphs as also as a source of inspiration. So we construct AI agents. An AI agent is basically this program that uses LLM as a reasoning kind of engine. So you can use LLM to make a decision. And we turn it more into a game, where not necessarily a game, but more into like this world where AI agent can live. Basically, we randomly select a node in this knowledge graph, and the agent is where it is located right now. It's, let's say, located at the node psilocybin. I'll say nodes, okay, I'm at psilocybin. These are the nodes that are neighboring. They're connected with psilocybin. This is where I came from, and it uses LLM to understand where to go next. And there are many ways you can actually implement this. We are experimenting with interest-based approach. We are basically trying to use AI agents to decide what is the most interesting connections to explore next, given that they are trying to optimize for these interesting, surprising connections in this knowledge graph. Or maybe you're trying to mimic the way we humans find information surprising, right? So you can also embed this curiosity into these agents as well while they're traversing this graph. But basically what we're trying to do is allowing agents to traverse or like walk through this graph and start looking for these chain of thoughts or chain of concepts. Different concepts are related together that can really bring me from this longevity to neuroscience domain, if we talk about the domains, right? Because it can traverse, it's a multi-hop traversing through a few different concepts that can maybe originate in one scientific domain, but end up in a different domain. So there's this cross-domain way of linking different aspects, right? So we allow our agents to walk and traverse this knowledge graph to basically looking for this interesting connection. And we can do it at scale because we are using AI and not humans for this. And then we have another system that basically judges of how interesting, how novel, how surprising is a given collection of, we call it subgraph. Subgraph is basically this connected concepts together, like a chain of connected concepts. And then we have this another system exactly that is judging how surprising or how novel it is, how novel this subgraph is. And this is like this game that one agent is trying to find interesting connections and the other one is judging it in order to lower the scale of the potential subgraphs, because not all of them did, because we inject randomness into this, there's a lot of potential subgraphs we can generate. Like there's a combinatorial explosion of possible paths it can take in order to limit the number of connections, that some of them are maybe not as interesting or some maybe are already done. We use another system that basically validates and judges how interesting, how novel, how surprising are these connections. Once we get this subgraph that actually paths this, that was generated by one agent that is just traversing this graph and then paths to another agent that is judging it. And once the subgraph is accepted, then it's being fed to another multi-agentic system that iteratively explores the space. It extends the context. Basically, it looks at the subgraph, start asking questions or creating proto-hypotheses. And these are being passed to another agent within the system that then explore the new research that has been done. And the new research that has been actually already investigating this. Maybe there's some evidence for or against, right? So it's sending agents to the world to start collecting evidence in order to have a better idea about the subgraph specifically. And this, in iterative fashion, it asks questions, it gets more papers. So like the literature review is being conducted actually live as they debate over this subgraph. Within this multi-agentic system, like this complexity of interactions between agents and asking new questions, getting more data is increased, and the output of the system is basically a hypothesis. That could be tested. So to answer your question is, we specifically use knowledge graphs and AI agents to walk through this graph to start looking for connections that might be underexplored. Imagine like in one paper, there's this information that X causes Y. And in another paper, completely different domain, they say, okay, Y causes Z, right? But these two papers are not talking to each other, and they don't know about the authors. They don't know even about this research. Maybe they're even using different vocabulary. But what it comes from here is that if X causes Y and Y causes Z, you can actually infer that X causes Z as well. So mathematically
But
speaking.
it can be a wrong correlation as well. That's why you need to verify.
Obviously, research is not perfect, and there's a lot of information and a lot of data, a lot of conclusions that are just wrong. You also have to account for this. So part of what we do is also we are embedding signals within the systems and within the knowledge graphs, basically where it came from, how many authors, like what authors were writing this paper, where is there any data, open data that was shared with the research? How many citations is for the research? There's all of these signal information that can be also used by an agent to decide how much to weight given evidence, for example, right? Or maybe how many papers we're writing about a specific collection, or whether there's a consensus between papers regarding a specific connection. Like, this is all important. Obviously, correlation doesn't, it's not causation. So I think you have to be quite careful where you also design these systems in order to account for this. So you should be taking as ground truth, basically, because it's all made by humans and there are mistakes. But you should also account for this and try to minimize this effect while working on these systems. Yeah, so the knowledge graph is just like an inspiration. So the entire context and another body of evidence is iteratively added later on when there's another multi-iterative system. The hypothesis generated system is taking it over and start working on a given subgraph to get more data, get more information, get more evidence. So yeah, this is a very iterative process.
Obviously, what I find interesting that you use the word curiosity. How can you induce curiosity in AI?
Right. Well, maybe important thing to say before is what curiosity is, right? It's like curiosity for me is this internal drive to learn something more, to expand my own understanding of something. And I think this is, it has to do a lot with how we humans live here in this world. This may be evolutionary trait as well, but it's really connected with us actually being in this on this planet. So this is actually I'm seeing in my son. Whenever I'm gonna go for a walk with him, he's stopping every time, picking up every stone, looking at it from every side. This is curiosity. He can actually interact with it. He can touch with this. I think curiosity is really connected with us living on this earth and interacting with everything. So how we can inject curiosity in the AI systems, or maybe specifically language models. What I would like to talk is how we inject anything into language models, basically training them and optimizing for this, right? What we are exploring right now is basically using domain experts like researchers to basically judge how interesting or surprising is a given connection for them. And we're collecting all of this information and then using reinforcement learning to kind of train the reward model of agent. So it can have this feeling of surpriseness as we humans have. And the theory is that this actually might steer down curiosity as well.
But if you optimize for a specific kind of curiosity, doesn't it stop being curious at some point? Because you said, okay, A is a curious hypothesis. You say, good, very good. So let's see how we can retrain our model to optimize for that. And then it starts to give you more or less same kinds of patterns, probably. I don't know. This is just a question.
Well, I guess we'll also see. That's one thing. But there's this concept in machine learning, it's bias variance trade-off, which actually comes together to overfitting or underfitting. So specifically when we are training models, so here specifically, we're not really training the model itself. We are training another model that is kind of a reward signal model that gives the signal of how surprising or how interesting or how curious might be a given subgraph or connection. Not specifically the model itself. But in general, when you're training a model, really want to overfit the model because it will be just able to recite everything from its internal parametric memory, and it would not be able to generalize. Like what we are aiming for is this ability to generalize together. Like this comes down to basically how this training is done, what kind of data you're using, how you're training for how long, and all of these little things and little and big things that you are doing while training these models. But yeah, obviously the goal, like this is something you have to be very careful about overfitting a model. But yeah, specifically here, we are actually more looking at training the reward model that can actually give signals back to agents while they are traversing this graph by kind of mimicking this curiosity from humans.
And I would use here a word creativity because technically what you are trying to engineer by inducing this curiosity is creativity. Do you perceive this kind of combinatorics creativity? And can it be compared to human creativity?
For me, creativity is something that is new, that is also surprising, and actually at the end is also valuable, right? So like these maybe three things is something that comes that I think of when I think about something that is creative. When you think about this, I think to a large extent we can think that the current AI models can be created, right? And so they are capable of creating something new, something surprising, and very often something valuable for us. However, I would say it's a little bit different to what we experience as a creative moments as humans. And I think maybe I would boil it down to motivation gap. When we talk about creativity in AI, AI still lacks its own goals and the curiosity that we talked about before, right? So this creativity is a little bit different. I mean, like as you mentioned, it's like combinatorial creativity. It can really connect a lot of different things in a lot of different ways, and we can actually train it to be aligned with what we want as well. However, it's still missing its own goals. Why it actually wants to do something. I think this is a big part of what curiosity is for humans, for our own motivations, our own goals that actually kind of drive this creativity from us. And I think like the current AI system is missing these components. It doesn't have its internal goals. It doesn't have internal motivation, which I think actually makes it a little bit different to what we have as humans.
Some people would argue, yeah, I've read an article, a recent article, that I think it was Claude, that the model started to lie for whatever reason and act very weirdly. And there was another one that they used an AI model to run, I think, a shop. Yeah, or no, that was a fridge. It started to pretend that AI model is an employee, started to write everyone on Slack that he will come to the office. So very, very weird hallucinations, strange ones. And like from looking at it, you would think that this person is probably mad, but this person has her goals and reasons.
Right. Well, I would say, from my understanding, the internal goals and motivation is still lacking from the current AI systems. And these things might be simulated, mimicked, but I would say this is still not where we are with the artificial intelligence. Speak of its own goals and motivation. But yeah, this is my view on this.
But do we, as humans, have actually our own goals and motivations? When you have a newborn baby, this baby has no idea what happens there. Baby can cry because something does not feel right. What doesn't feel right? Somewhere in the body, there is an instinct of survival. If I don't eat, I am hungry, I'm starting to shut down, I need energy. What I can do, I can shout, yeah, and maybe someone will come and save me. So for baby, this goal comes from the instinct of survival, yeah, and it's not a goal that this person, like, I will pursue a PhD. This is something very basic. And then later we grow older and there is a society around us, there is a family, there are friends, yeah, so all of that also creates some kind of social pressure, which often affects what we want in life. So from where our goals come from. Maybe humans are also not that independent thinkers as we would think.
No, 100%. I mean, I think I mean, like we are touching on the question of free will. So I'm not trying to say here we as humans are like completely free, independent thinkers, and everything here is because of our own goals that we are fully in control of, and it's coming from internal our personality, and it hasn't been influenced by anything else. That is not what I'm trying to say. What I'm more trying to touch on is that we do have this instinct of survival, for example, and this is an underlying goal that actually kind of forces us to live through this world. Just this goal of survival. AI does not have this. I mean,
Doesn't it?
we can. I mean, it then maybe also comes with the question of like what consciousness is. I would say, yeah, I mean, like, I think there's not really a good, answer here because we just don't know, we don't understand our own consciousness. It's really hard to say whether AI is conscious and whether it has goals. Like, we don't understand ourselves, and we already are interacting with these systems that are very often smarter than us. The amount of knowledge they contain and always certain also often reasoning that they can perform over their knowledge. It's but coming back, we don't understand really ourselves and our own motivations and our own goals, our own consciousness. So it's also really hard to say to have these opinions about artificial intelligence systems. I think like this drive for survival that we have as a species is something that is really hard to replicate. You can turn off the computer or like you can turn off the entire data center and you can turn it on back later. Cannot really turn off a human. At least for now, I haven't heard about anything. If you did, let me know. I might use it. But I mean, like just because of this, the concept of death and the understanding that things are finite. I mean, this is a huge drive for a lot of internal goals that we might have and our motivations that we might have as well. And about the way we understand the world, the way we experience it, and the way we interact with it. Whether LLM, because we are mostly talking about LLMs here, it can understand this. I mean, you can definitely simulate this for sure because they're operating with text. They can learn what people are writing about it. I'm not sure if at this point in time they can really understand it. I think really this is what we talked before. There needs to be perhaps a different way of how these systems are built, of how they're interacting with the world, maybe about them understanding how things are finite, about maybe mortality is the key. I mean, I don't know, I'm just putting out ideas. It's a very complex topic. And I think because of our own limitations in understanding who we are as a species and how we work, it's even harder to answer these questions about artificial systems, but also about animals, right? I mean, before we actually are able to say whether AI can be conscious, maybe we should actually start thinking. I'm sure people are thinking about it, and there's been a lot of opinions about this as well, but I don't really think we can really nail this down because this is not really a testable thing that can we conduct an experiment, but to see whether animals are conscious as well and like what consciousness is actually. Like because we don't really know, and this is really a hard problem for us, like hard problem of consciousness. I mean, it's really also hard to be able to say about species that are not our own. It's direct access to the way they experience our world, or whether they do have this subjective experience. Because the difference between consciousness and not consciousness is about whether you can get from just purely processing information to having a subjective experience of feeling something that happens, like a qualia. Where is this threshold where you stop just processing information about the world around you and you started feeling like having this sensation, it feels like something. And maybe whether this makes any sense at all to ask this question, maybe this is just consciousness might be just an artifact also of how brains work. Our brains are constantly trying to predict things. They're trying to predict the world, the world model that we live. So consciousness might be also an artifact of this, that is just like a byproduct of brain trying to constantly predict things that might happen. Whether consciousness is actually important at all, maybe this is something that is now we are dealing with and struggling with to understand. Maybe it's not even important for AI to be really efficient and productive and to take over the world. That's the last thing I said. Yeah, very metaphysical stuff. But I mean, it's really hard to answer these questions being human and not completely understanding ourselves.
Once a philosopher as a guest of this podcast. And we were also talking about AI and consciousness. And he was like, yeah, finally, I know why I got this degree, because currently everyone is super curious about qualia and consciousness. And I mean, is AI thinking and feeling itself as a, I don't know, as a personality or whatever. But I want to ask one last question because we are very much over time.
I have.
But it's really a very interesting discussion. Emergence. So I've read last year a very interesting book about emergence that posits a theory that at least living beings exist just on different levels of complexity of consciousness. And humans just have this very high level of complexity that results in being what we call conscious. However, animals and plants and maybe even something else, they also have some degree of consciousness that is, I would say, correlated to the level of complexity of their system. So practically their neural network, literally. And the idea is that at certain level of complexity, there is emergence, that system evolves and becomes more than a sum of its parts. And consciousness is a byproduct of that. Do you think that at some level of complexity of AI, that really may happen and this puzzle will just fall into place?
All right. I think I know this theory or like way of looking at the consciousness. I think it just basically states that the consciousness is on a spectrum, and the more complex system is, the more conscious it is. It kind of solves the hard problem of consciousness because it just doesn't say there's no consciousness and then it comes, but it actually says that it builds up. So like it starts, I think, even with even like these atomic parts already have some level of consciousness. Yeah, but this is just like a one way of looking at consciousness. It's also not testable. We cannot really test whether electron has some level of consciousness. I guess we could probably maybe see this if we are able to see consciousness in very complex systems, and by saying that previous systems are not conscious, right? But then also it gets also complicated because how would you be able to say something is not simulated but it's actually conscious? Like when you're talking to an AI system and you're asking, hey, are you conscious? It might tell you, no, I'm not. I'm just AI assistant being here to help you, right? Because this is basically how we train it to interact with you. Or when without this post-training alignment, but maybe just train on the internet where people actually write a lot of stories about AI becoming conscious and stuff. Maybe will tell you, yes, I'm conscious, you know? And then how do you know, like even if we get to this point, it's not just simulated, but it's really stemming from the subjective experience of the system. I mean, this it can be tested as long as you are not living this subjective experience. Everything else can be simulated. And I think maybe also this comes to a part that we cannot be really sure as well if any other one is actually conscious.
This is what I wanted to say. I mean, you have no idea. Maybe I'm a robot.
Maybe, maybe there's a lot of bots living around us.
Yes.
So I think I don't really have an answer to this. Because I'm also not 100% sure how we'll be able to test it. The answer if we cannot test it. So it's not really a theory then. This is my view with given the information I have currently. Yeah, I think this is really interesting. Just the discussions about consciousness in general are so interesting and so metaphysical because we cannot also really test them so well. Yeah, I mean, I think I don't really have an answer for this. Whether with enough complexity we can reach the consciousness, or there's something else. I think if I have to give one answer to this, I think complexity is necessary, but not sufficient condition for this. Maybe there's still something else that might be needed for this, and it's not maybe complexity itself, but it's definitely necessary for this conscious experience that we are experiencing, or like we as humans know. But I would be probably skeptical and say this is not sufficient for consciousness to.
Should be a secret sauce.
I would like to believe there is a secret sauce to it, and that it's kind of special.
Yeah, imagine how awful it would be if there is no secret source. So
Yeah.
humans are like, yeah, we are the only conscious creatures at this planet, and then there is no secret source, and you can just engineer consciousness. That would be a failure.
Well, actually, I think we are not the only conscious species here. This is like my personal view. But I think like there is actually a spectrum, maybe like the theory you mentioned is actually kind of extreme, but like it cannot be verified, so it's also hard to say. But I would say many animals have some kind of subjective experiences. We see this world. So I guess we're definitely like I wouldn't think we are the only conscious being on this planet. And speaking about the universe at large, I would say the chance of us being the only conscious beings is going to zero. The further we go in the universe. But yeah, that's just my personal view on this.
This inspirational note, let's wrap it up. So, how can people stay informed about your projects and support them?
Right. So talking about BeeARD, BeeARD.ai, there are also a documentation that describe our philosophy and our. Specifically, we are also present on social medias like Twitter, where we have our agents posting their journeys through the knowledge graph, and they write kind of in the style, today I learn about something, and they write about new interesting subgraphs that they visited. These samples are later on being passed to the generated system that works to create a scientific hypothesis. But these subgraphs and the story behind these subgraphs is actually posted on social media as well.
Cool. I will go and read.
Yeah, so it's BeeARD AI on Twitter. And then what we created also with our friends from Coordination Network, we created HypeGen. HypeGen is kind of a social media platform, but for AI agents outputs. We were thinking of like the biggest impact of anything that became created by AI at this moment is when real humans are seeing this and actually can perform experiments, at least to a large degree. So we were thinking, what would be the best way for outputs of our agentic systems for how humans could interact with them. And specifically here, we are thinking about scientists. So our idea is that everyone knows and everyone is somehow familiar with social media. So we created this the social media based on ad protocol that is powering Blue Sky, for example. A social media where only agents can post stuff. They can post for now hypotheses and subgraphs, and real humans and only real humans, so no other AI agents can interact with them. So they can comment on it, that can put emojis, basically whether they like it or not, so reactions. They can comment on the hypotheses. They can actually take hypotheses, and if they like it, they can actually perform an experiment. In the future, we would like to also turn these systems to also have ways to provide grants for this research as well. It's kind of a closed loop that the AI agents, they come up with these new ideas, hypotheses. The scientists are interacting with them, and based on the feedback it gets from real scientists, the AI agents can actually prioritize which research could be the most interesting, the most possible to perform, and most impactful and most effectual. And they could provide grants for making this research a reality, and so to provide researchers with funding to accomplish these researches as well. So this is HypeGen AI. Yeah. So these are definitely places you can find our agents or outputs of these agents being posted.
Wonderful. Thank you so much. That was a wonderful conversation.
My pleasure.
Yeah, and I'm wishing you a great evening ahead.
Thank you.
Yeah, thank you. Bye bye.